73 from chapter 13. It's one of my favorite types of problems. We have a car going over the hill and we're looking for the maximum speed at which the car can pass over the top point A. The car has a mass M, and still maintain contact with the road. And then if the car maintains this same speed, what is the normal reaction the road exerts on the car when it passes the lowest point on the road, which is B. We have the radius of curvature, which is R. So we're starting off at point A, and the tangential direction is the direction the car is going in. So we have the tangential direction, and normal is pointing in towards the center of the circle, which at point A is downward. However, sometime later when we're at point B, the tangential direction is still to the right, but the normal direction is in towards the center of the circle, so that's now pointing up. At some point here where we have an inflection point, the radius of curvature goes to infinity, and at that point you can't really say whether the normal direction is this way or this way because it's straight there. So we have a force of gravity pointing downwards at point A. We have a force of gravity pointing downwards at point B. At point A, we have no normal force because we're going as fast as we can, but just barely maintaining contact with the road. So if we went any faster, we would fly off the road, so the normal force is going to zero at the max speed. At the lowest point on the road, however, we do have a normal force. Okay, so at point A, the normal force is equal to 0, and I take a look at the equations that I have here. I have the force of gravity going in the normal direction, and so sum of the forces in the normal direction is equal to mass times the acceleration in the normal direction, which is v squared over rho. In this case, the radius of curvature is r. So we have mg is equal to mv squared over r, and so the maximum speed at which we can go without flying off of the road is the square root of g times r. At the lowest point B, we sum up the forces in the normal direction. Now it's n minus mg because, compare this and this, the normal direction has changed and now the positive direction is upward. And so then we're solving for n when we have our speed is the square root of gr. So we get 2 times m times g for the normal force. What I think is even more interesting is if you wanted to try, let's say, continuing like this and drive your car upside down here. Now the normal direction is pointing in towards the center of the circle. This is the tangential direction, and you have a force of gravity pointing downward. If you have a normal force, the normal force would also be pointing downward. The faster you go, the greater the normal force is, but if you go too slow, you're not going to stay on the road, you're going to fall. So rather than finding the maximum speed at which you can go without losing contact with the road, here we would find the minimum speed at which you could go without losing contact with the road. So in this case, if you go any faster than this, you're in trouble. In this case, if you go any slower than the speed that we're going to find, you would be in trouble. So the normal force is equal to 0. So we just have a force of gravity acting in the positive normal direction, which gives us the same equation that we had up here. So we have the normal force is equal to 0, mg is equal to mv squared over r, and so we actually get v is equal to the square root of g times r, which is the same speed that we got up here, but here it was a maximum speed and here it is a minimum speed.